I am here to discuss the measures of central tendency and dispersion. For the measures of central tendency, we are after the value that will represent our data. It can be the value that occurs most frequently, and that is the mode. Or it can be the central value of an ordered distribution, and that is the median. Or we can make use of the exact value for each entry, and that is the mean. For our example problem, we have here the one-way commuting distances in miles for 60 workers in downtown Dallas. As you can still remember, we have used this already in our previous topic, that is in organizing data. Okay, so again, how are we going to arrange this? Raw data. Okay, we can make use of the stem and leaf display to make it easier for us. Okay, so this is our arranged data, or we can call it the ungrouped data. Okay, so from this data, what is our mode? Okay, that is the most frequent value. Okay, we have here 12 and 16. So we have there two modes, 12 and 16, and that is called bimodal. Okay, then for the median, we have there n over 2, that is 60 divided by 2, we have there 30. The 30th place or the 30th value is 15. Okay, so 15. Well, in other books, we have there if our n is even, then we need to add the two values at the center, then divide it by 2. Okay, it's also right. Okay, so but since our median should be equal to our quantiles, that is the second quartile, the 5th decile or D5, and the 50th percentile, and then I decided to make use of this formula. Okay, n over 2. Then we have there our mean, that is the summation of x over n. That means we need to multiply all the values in this data, or this data, divided by n. Okay, or we can make use of the calculator technique, that is mode 3 1, then input all the values. Okay, and then shift 1. Okay, then 4. This is var. Okay, so you can see there 2 and 4. Okay, 2 is the mean and 4 is the sample standard deviation. Okay, so later we're going to use this. Okay, so of course for this data, I use the calculator technique to compute for my mean. Okay, so for the mean, we have there 17.52. Okay, so 17.52. For the resistant measure, it is one that is not influenced by extremely high or low data values. This extremely high or low data values is also called outliers. Okay, so in our example, as you can see, our mean is 17.52. Our lowest value, that is 1, and our highest value, that is 47, is very far from 17.52. Okay, so let us say I want to trim it. Okay, so trimmed mean is a measure of a center that is more resistant than the mean but still sensitive to specific data values. Okay, it removes the outliers. Okay, so how are we going to do that? For our example, Okay, so let us say I want to compute for the 5% trimmed mean. Okay, so first is compute for the 5% of your n, and 5% of this is 3. Okay, so what we need to do is to remove these first 3 values and then the last 3 values, and then again compute for the mean. Okay, so again use your calculator technique. We have there 16.81. Okay, for the weighted average, okay, so suppose your midterm scores or test scores is 83 and your final exam score is 95. Using the weights of 40% for the midterm and 60% for the final exam, compute for the weighted average of your scores. So if the minimum average for an A is 90, will you earn an A? So let us compute for the weighted average or the weighted mean. So we have here, weighted average is 83 times 0.4 plus 95 times 0.6 divided by 0.4 plus 0.6, and that gives us 90.2. Okay, so will you earn an A? Of course. Okay, next is for the measures of variation, okay, or dispersion. Okay, so from the word itself, it measures how varied or how dispersed our data. Okay, so again, the lower the dispersion or the smaller the dispersion, the better. Okay, so for the range, that is the largest value minus the smallest value. For our variance, we have here the variance for sample and variance for population. What is the difference between the two? This one. Okay, so for the sample, we have here our x values, our mean. Okay, let get the summation of x minus x bar squared divided by n minus 1. That is for the sample. And for the population, we have there the summation of x minus mu squared over n. Okay, and of course, you just get the square root of this variance, and that is our standard deviation. For our example, okay, so Big Blossom Greenhouse was commissioned to develop an extra large rose for the Rose Bowl parade. A random sample of blossoms from hybrid A bushes yielded these diameters for mature peak blossoms. Okay, so this is our data. So here, let us make use of this to illustrate how significant is our standard deviation. Okay, so for this data, let us first compute for the mean. Okay, the mean is 6, and of course the standard deviation is 3.07. Okay, so there is another hybrid. Okay, Big Blossom Greenhouse gathered another random sample of mature peak blossoms from hybrid B. The 8 blossoms had these weeds. Okay, so in inches, we have here our data. Okay, our mean for this data is also 6. Okay, so if you're going to choose between hybrid A and hybrid B, what are you going to do? They have the same mean. Okay, so let us compute for the standard deviation of hybrid B. The standard deviation of hybrid B is 1.07. Okay, that means this has less variation, or the measurement is less dispersed. This is better. So, for our example of this one-way commuting distances in miles for 60 workers in downtown Dallas, let us compute for the standard deviation. Okay, here we have, again, make use of your calculator technique. Instead of choosing 2, choose 4. Okay, so we have there 11.72, and then we have our variance, that is s squared, or just square 11.72. We have there 137.37. Okay, then of course, don't forget for the range, we have there 47 minus 1, that is 46. So for the coefficient of variation, it expresses the standard deviation as a percentage of the sample or population mean. Of course, we need what? A lower coefficient of variation. Okay, so we have here, this is for the population. This is for population. What about for sample? Of course, CV is equal to S over X bar times 100. Okay, this is for the sample. And let us compute for the coefficient of variation of the two roses. Okay, so we have here for hybrid A. Okay, what is our coefficient of variation? The standard deviation for hybrid A is 3.07 divided by the mean of 6 times 100. It gives us 51%. For hybrid B, we have there our standard deviation is 1.07 divided by 6 times 100. That is 17.83% only. So this is better. Okay, choose hybrid B. Okay, next is for the Chebyshev's theorem. Okay, so for any set of data and for any constant k greater than 1, the population of the standard, or the population or the proportion of the data that must lie within k standard deviation on either side of the mean is at least 1 minus 1 over k squared. Okay, so using that formula, these are the results. Okay, so for any set of data, at least 75% of the data fall in the interval from mu plus minus 2 standard deviation. We have at least 88.9% of the data fall in the interval from mu plus minus 3 standard deviations. And at least 93.8% of the data fall in the interval from mu plus minus 4 standard deviation. Again, okay, this is from the formula 1 minus 1 over k squared. Okay, so let us say this 75%, that is 2 standard deviation, that is 1 minus 1 over 2 squared, and that is 0.75. Okay, so that's it. For our example problem, the East Coast Independent News periodically runs ads in its own classified section, offering a month's free subscription to those who respond. In this way, management can get sense about the number of subscribers who read the classified section each day. Over a period of 2 years, careful records have been kept. The mean number of responses per ad is 525 with a standard deviation of 30. So determine the interval about the mean in which at least 88.9% of the data fall. So this is where this is mu plus minus 3 sigma. Okay, so we have there 525 minus 3 times 30 to 525 plus 3 times 30. We have there 435 to 615. So this is our interval. Next, Students Who Care is a student volunteer program in which college students donate work time in community centers for homeless people. Professor Jill is the faculty sponsor for this student volunteer program. For several years, Dr. Jill has kept a careful record of the total number of work hours volunteered by a student in the program. Each semester, for students in the program, the mean number of hours was 29.1 each semester, with a standard deviation of 1.7 hours each semester. So, find an interval A to B for the number of hours volunteered in which at least 75% of the students in the program would fit. This is where mu plus minus 2 standard deviations. Okay, so we have there 29.1 minus 2 times 1.7 to 29.1 plus 2 times 1.7. And we have there 25.7 to 32.5. This is our interval. Next is for the mean and standard deviation of group data. Okay, so the basic plan here is as follows. Make a frequency table. Okay, compute for the midpoint and call it X. Then count the number of entries in each class and denote it by F. Okay, that's the frequency. Add the number of entries from each class together to find the total number of entries and in the sample distribution. Okay, so for the sample mean of a frequency distribution, we use this formula. Okay, so we have here our midpoint. This is our frequency. Okay, and of course this is our n. Then here for the standard deviation, we have there summation of x minus x bar squared times f over n minus 1. So we have here, this is our midpoint. This is our mean. And of course, this is our frequency. Okay? Or you can make use of your calculator technique again. Okay? The first thing to do is you turn on your frequency. Okay? So how are you going to do that? Shift mode, and then arrow down, then choose stat. Okay, then you will be asked if you want to turn on your frequency. Turn it on, that is 1, choose 1. Okay, then again on, then mode 3, 1. Then again input all your values. Okay, you're going to see this. Okay, in your calculator you have your x and this is your f. Okay, you just need to input all your values there. Okay, and then after that press on and then shift 1, then 4, and then again you can choose 2 for the mean and 4 for the standard deviation. Okay, okay, so for our example, okay, so this is our group data. Again, our class width here is, as you can still remember, 7. Okay, so let us compute for the mean. That is summation of xf over n if you want this to be done by longhand computation, or you can make use of your calculator technique. That is, this is x and this is f. Okay? So for this one, of course, I use the calculator technique. So for this one, the mean is 17.65. Okay? Of course, the standard deviation is 11.7. Square it for the variance, that is 91. Of course, let us compute for the coefficient of variation. That is 11.7 divided by 17.65 times 100. That is equal to, we have 66.29. Okay. Then, from this group data, okay, let us compute for the median. Okay. So, how are we going to compute for the median? So, first is compute for n divided by 2. N is 60 divided by 2, that is 30. Okay. So, 30 is, we need to locate 30 in this column. Okay? Column, yeah. So, 30 is located where? It is between 29 and 43. So, 30 minus the value above, that is 29, okay, divided by what is the frequency below. Okay? So, we have here 29, 43 is the value below. What is the frequency? That is 14. Okay? Multiplied by the class width plus, okay, so that is the lower class boundary located where? Here, at the frequency row. Okay? So we have there 14.5. So for the median, we have there 15. Okay, again, n over 2, that is 30. Look for 30 at the column of less than cumulative frequency. 30 is located in between 29 and 43. So 30 minus 29 divided by, okay, so the value below 30 is 43. And the frequency at 43 is 14. Okay, so at 14, we have there the lower class boundary is 14.5. Okay, so we have there 15. Sorry for that. Excuse me. We have here mode. Okay, for the mode, okay, so look for the highest frequency, that is 18. Okay, 18. Then minus the value above 18, that is 11, divided by 2 times the highest frequency, that is 18, 2 is a constant, minus the value above 18 minus the value below, that is 14. Multiplied, of course, by the class width plus the lower class boundary at the row of the highest frequency, that is 7.5. Okay? So, our mode is 11.95. Okay. What about the range? Okay. So, range is this one. The upper class, the highest class boundary minus the lowest class boundary. We have there 49.5 minus, we have 0.5, that is equal to 49. Okay? Next, quartiles. Okay, and the quartile deviation. For the quartiles, these are values that divide the list of numbers into quarters, meaning 4. Okay, so the quartile deviation is half of the distance between the third and the first quartile. Okay, this one. Okay, so for ungrouped data, that is simply n over 4 for the first quartile. Okay, and for the third quartile, that is 3n over 4. Please take note of this. If you're going to compute for the second quartile, so that's Q2, this 2, that is 2n over 4. Okay, and also remember that Q3 minus Q1, this is interquartile range. Okay, for the group data, how do we compute for the quartiles? Of course. Anyway, that is quantiles. Quantiles, we have quartiles, percentile, and decile. Okay, so for this quartile, okay, as you can see, this is also the formula that we use for the median. Okay, it's just the same. The only difference is this one. Okay, then for the percentile, the kth percentile is a value in a data set that splits the data into two pieces. The lower piece contains k% of the data, and the upper piece contains the rest of the data. That is 100 minus k. Okay, because the total amount of data is 100%, and k is any number between 0 and 100. Okay, so the median is the 50th percentile. Okay, the point in the data where 50% of the data fall below that point and 50% fall above it. So for ungrouped data, we use this formula. Let us say I want to compute for P10, then that would be 10n over 100. Let's say P90, we have there 90n over 100. Okay, and then again for group data, this is just the same as computing for the median. Okay, the only difference is this one. So for the decile, each of 10 equal groups into which a population can be divided according to the distribution of values of a particular variable. If quartiles is by 4, percentile is by 100, then decile is by 10. Okay, so for ungrouped data, we use this formula. So let's say I want to compute for D3, that is 3n over 10. Let us say D8, we have 8n over 10. And again, for the group data, it's just the same as computing for the median. Okay, so the only difference is this one. Okay, so let us compute for the quantiles for this data. Okay, so for the Q1, that is n over 4. So that is 60 divided by 4. We have there 15. 15th place is where? You have your 6, 12, 13, 14. Oh, 15. Yeah. 12, 13, 14, 15. This is your Q1. For Q2, we have there 2n over 4. And that is 2 times 60 divided by 4. We have there 30th. Okay, that's why I told you that median is the same as the second quartile. It is also the same as D5 and the 50th percentile, or P50. Okay, so 30th value is, we have there 15. This is Q2. Q3 is 3n over 4, and that is, we have 3 times 60 divided by 4, we have there 45th. So we have here 15. We have there 24. Okay? Yeah, that is your Q3. Okay? Then we have there D3. Let us say I want to compute for my D3. 3n over 10. And that is 60. 3 times 60 divided by 10. We have there 18. So 18th place. If this is 15, this is our D3. We have there 10. D5 is D5 is 5n over 10. That is 5 times 60 divided by 10. We have there 30th. That is 15. This is D5. Okay? Then let's say I want to compute for D8. That is 8n over 10. And that is, we have 8 times 60 divided by 10. That is 48. And we have here 45, 46, 47. 26. Okay? This is your D8. Okay, what about P? Let's say P10. Okay? P10 is 10n over 100. So 10 times 60 over 100 is 6th place. Okay, we have there 4, P10. Let's say P50. That is 50n over 100. That is 50 times 60 over 100. And that is 30th place. This is 15. We have there P50. Okay? Let's say P90. We have there 90n over 100. That is 90 times 60 over 100. We have there 54th. Okay, 54th place. Okay, so we have here 48. Here 36. This is our P90. Okay, so next is we can compute now for the skewness and kurtosis. Okay, when we say skewness, is a measure of symmetry, or more precisely the lack of symmetry. Okay, so for the skewness, the formula is 3 times the mean minus the median divided by the standard deviation. Okay, so skewness is used to determine the normality of the data. If skewness is 0, that means there is no variation then, or it is at the center. Okay, so if it's 0, then the data is said to be normal. Okay, so in say skewness, it can be positively skewed or it can be negatively skewed. Okay, so this positively skewed and this is negatively skewed. If the mean is greater than the median, then it's positively skewed. If the median is greater than the mean, then it's negatively skewed. Okay, so for the skewness of our data, we have there 3 times what is our mean, our mean is 17.65. No, I need to use the ungrouped data. Okay, so for the skewness, we have there the mean is 17.52. Okay, minus the median of 15 divided by its standard deviation, which is 11.72. Okay, so for the skewness, we have there okay 0.6451. Okay, so it's positively skewed. Okay, another one or another measure is the kurtosis. Okay, so for the kurtosis, it is a measure of whether the data are heavy-tailed or light-tailed relative to a normal distribution. Okay, so this is computed by using the formula kurtosis is equal to Q3 minus Q1 divided by 2 divided by P90 minus P10. Okay, remember, this is our quartile deviation and this is our interquartile range, Q3 minus Q1. Okay, so in kurtosis, we have there, okay, we can have this distribution. This is negative kurtosis or platykurtic. We can also have this distribution, that is the normal distribution, that is mesokurtic, and this one, this is leptokurtic. Okay, or the positive kurtosis. Okay, by the way, we are going to discuss this later on in normal distribution. Okay, so kurtosis should be 0 to claim that the data is normal. Okay, so for the kurtosis of our distribution, we have our Q3 is 24 minus our Q1 of 9 divided by 2 divided by our P90 is again 36. 36 minus P10 of 4. Okay, so what is our kurtosis? Okay, we have there 0.234. Okay, okay, what about for the group data? Okay, so I have already computed for the mean. Okay, let us say I want to compute for the let's say first quartile. Okay, so for this one, we have Q1 is again n over 4. So n over 4 is 60. 60 divided by 4 is 15. Okay, so 15, we need to locate 15 here. Okay, 15 is in between 11 and 29. So minus 11. So 15 minus the value above divided by, what is the frequency? Below we have there 18 multiplied by 7, the class width, plus what is the lower class boundary? Okay, 7.5. And this is equal to, we have 9.06. Okay, let us say I want to compute for Q3. Okay, since Q2 is also the same as the median, we have there Q3 is 3n over 4. And that is 3 times 60 divided by 4 is 45. Okay? So where is 45? It's between 43 and 50. So 45 minus the value above, that is 43, divided by the frequency below, we have there 7. Okay, times 7 plus the lower class boundary of 21.5. And that gives us Q3 is 23.5. Okay? Then, let us say I want to compute for P10. Okay, P10. We have there, okay, so 10 times 60 divided by 100 is 6. Okay, so where is 6? Okay, so that's above 11. Okay, so 11. No, so there is no value above 6. So that is 6 minus 0 divided by, okay, the frequency below, that is 11 times 7 plus the lower class boundary, we have there 0.5. And it gives us P10 is 4.32. Okay, then what about, let's say, P90? Okay, P90, that is 90 is 54. Okay, that's 90 times 60 divided by 100 is 54. Where is 54? In between 53 and 57. So that is minus the value above 54 is 53. Okay, so divided by the frequency below, that is 4 times 7 plus, okay, we have it here, our lower class boundary 35.5, and that is equal to, we have 37.25. Okay, so for the mean deviation, okay, so for the mean deviation, it is simply the summation of the absolute value of x minus x bar over n. So for this one, the computed mean deviation for our ungrouped data, that is the one-way commuting distances, is 9.122. That is simply the x, okay, values minus the mean. Okay, and then of course for the group data, okay, there you go, you have it here. We have there, this is our x, this is our f. Of course, our x bar is equal to 17.65. Okay, so you need to subtract, since mean deviation is equal to the summation of the absolute value of x minus x bar times f over n. So we have it here, we have, this is our midpoint, x minus the x bar of 17.65, absolute value of that multiplied by the frequency. Okay, you get the sum and then divided by n. It gives us 8.995. Okay, next is the relative measure of dispersion. The relative measures of dispersion are used to compare the distribution of two or more data sets. Okay, so this measure compares values without units. So these are the common relative dispersion methods. So for this one, we have here the coefficients of dispersion are calculated along with a measure of dispersion when two series are compared, which differ widely in their averages. So the dispersion coefficient is also used when two series with different measurement units are compared. It is denoted as CD. Okay, so the common coefficients of dispersion are, we have your range, the quartile deviation, the standard deviation, and the mean deviation. And these are the formulas. Okay, then for our ungroup, Okay, let's say for the ungrouped data, okay, I'm using the example of one-way commuting distances. For the range, we have there 47 minus 1 over 47 plus 1, and it gives us 0.96. Okay, then for the quartile deviation, we have there our third quartile is 24 minus the first quartile of 9. This is 24 minus 9 divided by 24 plus 9, and it gives us 0.45. Okay, then for the standard deviation, actually it's the same as the coefficient of variation. Okay, we have there 11.72 divided by 17.52, that is equal to 0.668 or 67. Okay, so for the mean deviation, we have there 9.122 divided by 17.52, that is our x bar, that is equal to 0.52. Okay, so for the group data, okay, so for the grouped data, you have there for the range, we have 49.5 minus 0.5 divided by 49.5 plus 0.5, that is equal to 0.98. For the quartile deviation, we have there 23.5 minus 9.06 divided by 23.5 plus 9.06, that is equal to 0.44. Okay, then for the standard deviation, we have there 11.7 divided by 17.65, that is equal to 0.66. Okay, and then for the mean deviation, we have there 8.995 divided by 17.65, that is equal to 0.51. Okay, then for the box and whisker plots, the quartiles together with the low and high data values give us a very useful 5-number summary of the data and their spread. A 5-number summary that includes the lowest value, the first quartile, the median, the third quartile, and the highest value. Okay, by the way, box and whisker plot is just the same as the stem and leaf display. It belongs to the exploratory data analysis tool. Okay, so how are we going to make a box and whisker plot? We draw a vertical scale to include the lowest and highest data values. To the right of the scale, draw a box from Q1 to Q3. Include a solid line through the box at the median level. Draw solid lines called whiskers from Q1 to the lowest value and Q3 to the highest value. Okay, so let us make a box and whisker plot for the ungrouped data. So we have our lowest value is our lowest value is 1 and our highest value is 47. Okay, so again, we first locate our Q1. What is our Q1? We have there 9. Okay, so this is Q1. Our Q3 is 24. Okay, so this is our box. Okay, what about the median? That is 15. This is 9. This is 24. And this is 15. Okay, then our lowest value is 1. And our highest value is 47. Okay, that is our box and whisker plot. Whiskers plot. Okay. Okay, so if you have any questions or clarifications, just send me a message. Okay, so that's all. Thank you very much and God bless.